Hello, my name is Patrick Fleming, and I will be recording on motion of a falling object for Lab 2 in Physics 1. How we're going to find the gravitational pull, the force per se, on an object is by using the formulas below, fundamental principles of physics that we're learning in class. So the first formula is how we're going to find the force pulled by two objects, one with mass 1, the other with mass 2, r being the distance in between. R is an abbreviation for radius, usually using this formula using the radius of the Earth as the distance. Also using the big G, gravitational force constant, which is 6.7 times 10 to the negative 11th. Next, we're going to find little g. Little g is usually used in planetary observations, finding the pull from a planet in certain situations. So how we're going to find that is by using the big G stated above, 6.7 e negative 11 times the mass of the object or planet divided by the radius of the planet squared, or the radius of the object squared. And with the little g, we can use our most general gravity formula, force equals mass times gravity. And this is how we're going to calculate the force of an object directed by gravitational pull. So next we need to find the position of the object affected by gravity. How we're going to do this is first finding the velocity of the object, first at rest, and then increasing acceleration downward due to gravity. We will find this by having F net as the force of gravity that we will compute in a previous formula. And then we can use the velocity final to find the final position, which will tell us the acceleration and how fast and how far the object is being displaced from gravity. So for my project, I used a 5-hour energy. I dropped it from approximately 3 feet high, or 0.5 meters high, and I had very good results on the acceleration of the object due to gravity. So when modeling using VIDLE, I first modeled my object without drag force. As we can see from this chart, without drag force, the estimations are going to be much higher than the actual observations. So how we can compute this differently is by modeling with the gray, having a drag force involved in the formula and in the Python modeling computation. As we can see, the top predictions are going to be slightly less, 0.15 meters, but that is alright because the final position will be much closer. So what does it mean? Examine the velocity versus time predicted by your models with and without drag. This is exactly what we just did before. The velocity versus time without drag was very off. It did not properly predict the position at the final point. It was slightly larger than the observation. With drag, you can predict much more accurately. Imagine that the object was initially thrown downward. Would the terminal velocity in this case be the same or different from the case where the object was initially dropped? The terminal velocity for objects is going to be the same no matter the initial velocity of the object. Basically, the larger the velocity gets of an object in the air, the larger the drag force of the object. So, as we can see from this video lab report, models with drag computations are going to be much more accurate. the force of gravity can be seen through many formulas and computational models on computers. And a object with zero initial velocity and an object with a large initial velocity are going to have the same terminal velocity. Thank you for stopping by.